And we're going to be moving into the central limit theorem. The scariest part of this section will be just the name, because it's a new name that we're hearing, central limit theorem. Here for number 1, this part is not really a question. It's a definition of the central limit theorem. I'm giving you guys what the central limit theorem says. So let's read this. If a sample size of n, where n is greater than or equal to 30, are drawn from any population with a mean mu and standard deviation sigma, then the sampling distribution of sample means approximates a normal distribution. The greater the sample size, the better the approximation. Okay, in English, as long as the sample size is at least 30, right, 30 or more, then we're going to say it's a big enough sample, so we're going to use the normal distribution, what we saw last unit and what we saw in our last lesson as well. Obviously, the bigger the sample, the closer we're going to be to our approximation. So that was simple. So let's read this here. If the population itself is normally distributed, then the sampling distribution of sample means is normally distributed from any sample size n. In either case, the sampling distribution of sample means has an a mean equal to the population mean. Okay, so here we have something about the mean, variance, and standard deviation. From the previous lecture, here it says what's the mean of the sample. I'm gonna say the mean of the sample, it is equal to the mean of the population. So whatever it is given as a mean for the population is the same mean for the sample. Now, here in my work, I'm not quite going to ask you guys I'm not going to give you the variance, but in other studies, we will do variances. So here, variance, it says, what's the variance? Notice I use sigma squared. What's the variance of the population, of the sample? What's the variance of the sample? Well, there's a formula. It is going to be the variance of the population. So remember here, the variance of the sample, it is equal to the variance of the population divided by n. And remember, n is how big is our sample. Now, a standard deviation of our sample is going to be the standard deviation of the population divided by the square root of n. Somebody might come and say, wait a minute, Mr. Leonzo, I remember from previous units, the standard deviation was the square root of the variance. Then I'm going to say exactly. Look, here we have sigma squared. What's the square root of that? Well, sigma. Here we have n for variance. What's the square root of that? Well, square root of n. So still, standard deviation is the square root of our variance. Now, any population we're given, right? Our population can have a graph looking like this. Any population, as long as the population, the sample is at least 30. So remember, that's what we read. As long as the sample is at least 30, it will look like a normal distribution. So we'll follow the idea of a normal distribution. It doesn't matter how the graph looked like, as long as the sample is at least 30. If our sample was normal to begin with, well, obviously stays normal. Now here, let's take a look at one question here, one sample. Cellular phone bills for residents of a city have a mean of $63. So I have here, it says the mean is 63 and the standard deviation of 11. So the standard deviation of 11 as shown in the following graph. Yeah, I see the mean here in the center, and the distance between 63 and 74 is 11. The distance between each of these spaces is 11, which means the standard deviation. So I see it on my graph. My random samples of 100 cellular phone bills are drawn. Okay, so the sample, my n, is 100. It is more than 30, so we're going to treat it as a normal distribution. So remember, random samples of 100 cellular phone bills are drawn from this population, and the mean of each sample is determined. Find the mean and standard error of the mean of the sampling distribution. Okay, so here it's just asking us, what's the mean of the sample? And it's also asking us, what's the standard deviation of the sample? Okay, now the mean of the sample is the same thing as the mean of the population. So my mean is going to be 63. Now, the standard deviation of the sample is not quite the same standard deviation of the population. Instead, I'm going to go kind of like, exactly what we did in the previous section. I'm going to go standard deviation of the population divided by the square root of n. Remember, n is how big is our sample. So in this case, I'm going to go 11 divided by the square root of 100. I know square root of 100 is 10, so I'm looking at this as 11 divided by 10, which is better known as 1.1. And that's it. That's all we're asking. We're being asked for. So as long as the sample is at least 30, remember 30 or more. In this case, the sample was 100. We're going to treat it like a normal distribution. Now, let's take a look at this older question here. The graph below shows the length of time people spend driving each day. You randomly select 50 drivers. So I'm going to say my population is 50. So that's more than 30. Age is 15 to 19. What is the probability that the mean time they spend driving each day is between 24.7 and 25.5 minutes? Assume that the standard deviation is 1.5. Okay, I don't quite see the mean, but I see it says you randomly select people that are ages 15 to 19, and then I see a graph here. Well, let me zoom in. What does this graph look like? It says time behind the wheel. The average time spent driving each day by age group. So people that are 15 to 19, their average is 25 minutes per day. People that are 20 to 14 spend about 52 minutes a day. People that are 25 to 54, their average is 64 minutes a day. People that are 55 to 64 years old, they spend an average of 58 minutes a day. And lastly, people that are 65 years or older spend about 39 minutes a day. So here, my group that I'm studying is 15 to 19. So I'm looking at this right here. And I know this is the average time spent on each day, 25 minutes. So I'm going to say the mean in this case will be 25. Okay, so they spend 25 minutes, an average. Now here it is asking me, what's the probability that they're going to spend, they're going to be driving between 24.7 and 25.5 minutes. Okay, I gotta do two different C-scores. Let me find the C-score for 24.7. And for that one, I'm gonna go 24.7 minus 25 divided by 1. Oh, I'm not gonna do 1.5, right? I have to find what's my probability of the sample. Remember how we do this? We go 1.5 divided by the square root of n. N is how big is my sample, right? In this case, 50. I'm gonna do this in a calculator. 1.5 divided by the square root of 50. It gives me a long decimal. In this case, my decimal that it gave me was 0.21213. I went to 5 decimal places. Okay, So coming back for my C-score, I'm gonna do 24.7 minus 25 divided by 0.21213. In my result, I'm gonna round it to 2 decimal places. Okay? So I'm gonna round this to 2 decimal places. When we see C-scores, we want 2 decimal places. In my case, I get negative 1.41. Okay. I was trying for 24.7. And my C-score is negative 1.41. Not bad. Let me try for the other C-score. Because remember I said I was going to try for 2 C-scores. I'm going to go 25.5 minus the mean, which is 25. And divide this by the standard deviation of the sample. Oh, I just figured that it was 0.21213. Okay, so do this. So let me figure this out. 0.5 divided by 0.21213, rounded to 2 decimal places. In my case, I get 2.36. Okay. So what I'm dealing with here, my C-score, in reality is, let's assume it looks like a normal distribution. My sample is big enough. The mean, right here in the center, the mean is 25. I'm checking for 24.7, not graph to scale, but I'm going to say 24.7 is somewhere over here. Like I said, it's not graph to scale. I just put a big space because I need space to write over here. So I don't want to put it too close to the 25 because I need space to graph there, okay? And then my 25.5 is going to be somewhere over here. Again, it's not graph to scale. I just gave myself some space in there. My 24.7 gave me a C-score of 1.41, a negative 1.41. Let me use my table. My table for probabilities here. And remember, I'm looking for 1.41. My C-score that I'm looking at for right now is 1.41. Up to the first decimal place, 1.4, I'm going to look at it somewhere here on the left. My second decimal place, this 0.01, I'm going to look at it over here on the top. So when I look at 1.4 and 0.01, that gives me that my probability for 1.41 is right here. Let me zoom in. You guys see it? My probability for 1.41 is 0.4207. Remember, what does this mean? What does this 0.4207 mean? Even give me a graph here. Is the distance between the mean and that C-score. If my C-score is positive, well, my C-score goes to the right of the mean. If my C-score is negative, well, my C goes to the left of the mean. However, the probability between the mean and my C-score, whether I go to the right or to the left, the area is 0.4207. What does that mean? Well, let me come back here. The distance between the mean and 24.7, my probability here will be 0.4207. That's what it means. Remember when we had 24.7, we got a C-score, and we used the C-score on our table to find our area here. Okay, how about here? What's the distance between 25 and 25.5? What is this area? What's this number? Well, based on 25.5, we got the C-score of 2.36. Well, let's use our table, 2.36. So when I'm looking at 2.36, that 2.3, I'm going to look for here on the left. the second decimal number, I'm gonna look for it on the top. Okay, so 2.3 here in the left is right here. Right, you guys see it, 2.3. My 0.06 is right here. You guys see it. So they meet right there. All right, I make this line. Okay, so I get 0.4909. Do you guys see it? So my C-score of 2.36 gave me my probability of 0.4909. Okay, let's come back to our work here. So I just found out that this area here, it is 0.4909. Now, do you see why 25.5? I didn't put it right close to the 25. I wanted to give myself some room to be able to write this number. The same thing with 24.7. I didn't put it too close to the 25. I wanted to give myself some room to be able to write. Okay, now here it says, what's the probability that it's in between 24.7? I see 24.7 and 25.5. So basically I'm asking, what is this probability? Well, just add them up. So 0.4207 plus 0.4909, I get 0.9116. That is it. It wasn't too hard, right?